All right, welcome to this calculus lesson, volume, finding volume using integrals. There's two ways to do that, two main methods of doing that. Volume with known cross-sections and volume with revolutions, where it's revolving around either a vertical or horizontal line. So this lesson is going to be about cross-sections, which in my opinion is a little bit easier, but takes a little more imagination as to what volume we're actually trying to find. So when you're doing this lesson on Delta Math, move this slider back and forth so that you can see the volume change as the X goes from left to right. So drag it all the way back and then drag it slowly from left to right to see the volume build. So with known cross sections, we just found area between two curves. So the physical 2D area between two curves. So these two curves, f of x, which is x squared minus 2, so that's the parabola, and g of x is 2x minus 2, that's just a straight line. So g of x is behind here. So in the last section, when we were finding the area between two curves, we were just finding this 2D area of this shape. So to do that, we took top curve minus bottom curve. So we're going to continue using that method, because what we're doing when we're taking top curve minus bottom curve, when I go to top curve, I'm going from the x-axis up to g of x. So what that's finding is the y value, or the height of that line. When I take top curve minus bottom curve, when I go up to the bottom curve, I'm getting that y value, which is the height at that x point of the bottom curve. When I'm taking the top height minus the bottom height, what I'm left with is the inside height. In top curve minus bottom curve. Volume, we're going to build off this idea. So if the region R is the base of a solid, so this region R is the base of the solid, such that each cross-section meaning a piece, like one piece perpendicular to the x-axis, meaning we're straight up and down from the x-axis, vertical from the x-axis, is an isosceles right triangle with a leg in the region R. So let's unpack that. An isosceles right triangle, well, we know it's a triangle. We know it's right, meaning it's 90 degrees. And isosceles means the two legs are the same length. The base and height are equivalent. Well, it told us that the leg is in region R. So meaning the triangle starts in region R. The base of the triangle is in region R. And now picture it coming up off the page, this 3D shape now. We're going to find the volume of this shape where the base is region R. So we're going to come up off the base with triangles, and when we integrate the area of each triangle, we add all the areas together, we'll have the volume of this shape. So the base is in region R. So what I need to find is the base in terms of my functions f and g. So the base in region R is, well, to find the length of that base, it's still top curve minus bottom curve. So in this case, g of x is the top curve, and f of x is the bottom curve. So this is my base. G of x is equal to 2x minus 2 minus f of x, which is equal to x squared minus 2. So my base is negative x squared plus 2x. And since it's an isosceles right triangle, this is also the height. Okay, so we have our intersection points, 0, negative 2, and 2, 2. So we're going to integrate from the intersection points, x equals 0 to x equals 2. The base and the height are both g of x minus f of x, simplifies to negative x squared plus 2x. And to find the area of a triangle, we take 1/2 base times height. So 1/2 times the base times the height. The base and the height are the same length, so it's squared, quantity squared. So we integrate to find the volume. So we're going to integrate the area to find the volume. Well, the 1/2 comes out front. We're going from 0 to 2. We have base times height, dx. Use your calculator to find this volume. Let me pull up my calculator so we can do it together. Okay, so to type this in, start with the 1/2 out front, math 9 to get the integral, definite integral to pull up from 0 to 2, and we have, I'm going to put it in the simplified version, negative x squared plus 2x, quantity squared, dx. Oh, I hit minus instead of negative. Yeah, I hit minus instead of negative. So the volume of that region is 0.533. Volume is units cubed. And it's the volume of this region coming off the base, creating isosceles right triangles with the same base and height from 0 to 2. Integrating the area adds all those areas together, creating our volume. Okay, next example. So what's going to change here is the shape of the cross section. We don't have to use isosceles right triangles. So here, let region R be the area enclosed by the function f of x equals x squared. The horizontal line y equals 2. The y-axis okay, so let's mark those. We've got f of x, which is x squared. We've got the horizontal line y equals 2. And the y-axis enclosing our region. So region R is in here. If the region R, this is now the base of a solid, such that each cross section perpendicular to the x-axis. coming straight up from the x-axis, we have a rectangle whose height is twice the length of its base in region R. So this time we have a rectangle coming up with its base in region R coming up off the page. And its height is twice the length of its base. So we're starting with a rectangle. This time we have a rectangle with the base in region R, and the height is twice the length of the base. So what we need to find is the base in terms of our functions f of x and y equals 2. The base is going to be equal to top function, which is 2, minus bottom function, which is f of x, and that function is x squared. So our base is 2 minus x squared. The height is 2 times the base. So the height is going to be 2 times that. Now we can integrate the area to find the volume. So setting this up, we're integrating the area of the rectangle. The area of the rectangle is base times height. The base is equal to 2 minus x squared, and the height is equal to 2 times 2 minus x squared. So this simplifies to 2 times the quantity 2 minus x squared squared. Now, using your calculator, you could find this point of intersection. Since we're starting at the y-axis, we know that x equals 0 at the y-axis, and then we need this x value as our upper limit. So we're starting at 0, we end at that point of intersection, integrate the area, and that volume comes out to be 6.034. Its volume, if we knew the units, would be units cubed. And one more. Let R be the region with area enclosed by f of x and g of x if region R is the base of the solid such that each cross-section perpendicular to the x-axis is a semicircle. The diameter is going through R. Okay, a semicircle this time. Semicircle is a half circle. And the diameter, which is the length all the way across, extends through region R. So to find the length of the diameter, this will be top curve minus bottom curve. Well, the top curve under there is going to be the straight line, which is g of x. The bottom curve is f of x. So the diameter is equal to 3x minus x squared. The area of a semicircle the area of a whole circle is pi r squared. So the area of a semicircle is going to be 1/2 pi r squared. Well, if the diameter is 3x minus x squared, then the radius is half of that. So the area that we're going to integrate is 1/2 times pi times this quantity squared. So here we have the area So here's the area of each semicircle. We can integrate this to find the volume. So 1/2 pi can come out front. We're going to leave this. Anything in terms of x has to stay inside. R squared under the integral. And then we're going to look to see what the boundaries are. We start at 0, and these two functions meet at 3, 9. So going from x equals 0 to x equals 3. And you can sub this into your calculator to find this volume, which should come out to 3.181 units cubed. This looks slightly different, only because they simplified the inside squared. So it would be top squared over bottom squared. 2 squared is 4, which would pull out. 2 times 4 is 8. That's where the pi over 8 came from. Then inside they just have the quantity squared as well. So they just pulled the other constant out. You can do that, or you can leave it as is. Your calculator will figure it out from there. All right, there's the lesson on using integration to find volume when cross sections are known. If cross sections are known, that means we know a geometric shape that's coming out of the base of the region inside the quadrant coordinate plane. We use the area of each shape, and then we integrate the area to find the volume between the 2 points of intersection.